The pitot-static system supplies both pitot and static pressure for the airspeed indicator, the altimeter, and the vertical speed indicator. Pitot and static pressure are usually sensed by a pitot head situated where it's not likely to be affected by turbulent airflow caused by projections from the aircraft skin. Some aircraft have static vents, which are separate from the pitot head. These are usually fitted in the side of the fuselage. Pitot and static pipelines within the wing and fuselage carry the pressure to the gauges on the instrument panel. An alternate static source is usually provided, the control valve for which will be mounted somewhere close to the instrument panel. With an unpressurized aircraft, if the alternate static source is from within the cockpit, then the pressure sensed will normally be lower than normal outside static pressure due to aerodynamic suction. It's inevitable that water will enter the pitot-static system, and it is just as inevitable that should that water enter the barometric instruments associated with the system, then they will suffer damage. To prevent the water getting too far into the system, drain valves are fitted at the lowest point in the pipeline. Part of the pre-flight check should involve opening these valves to allow any moisture to escape. Ensure that the valves are closed properly after the check. An aircraft at rest on the ground in still air is subject to normal atmospheric pressure, which bears equally on all parts of the aircraft. This ambient pressure is known as static pressure. An aircraft in flight, while still subject to the static pressure at its flight level, experiences an additional pressure on the leading edges due to the resistance of the air to the aircraft's movement. This additional pressure is called dynamic pressure, and its value depends both on the speed of the aircraft through the air and on the density of the air. The leading edges, therefore, encounter a total pressure consisting of static plus dynamic pressures. This total pressure is also known as pitot pressure. An open-ended tube, parallel to the longitudinal axis of the aircraft, is used to sense the total pressure, that is, static pressure plus dynamic pressure. This device is a pitot tube, which is mounted in a pitot head. The open end of the tube faces into the moving airstream, while the other end leads to the airspeed capsules in the airspeed indicator. The moving airstream is thus brought to rest in the tube, so generating the extra dynamic pressure, which, together with the static pressure already in the tube, provides the required total, or pitot pressure. The static and pitot sources may be combined in one pressure head, the static tube surrounding the pitot tube, with separate pressure lines leading to the pressure instruments. An electric anti-icing heater coil is usually incorporated, which is controlled from a switch in the cockpit. It will be appreciated that, if due to turbulent airflow in the region of the pitot-static heads, the pressures sensed are not truly representative of the pitot and static pressures, the pressure-dependent instruments will not read correctly. The error involved is called position error, or alternatively, pressure error. Approximately 95% of the position error associated with a combined pressure head is produced by turbulence about the static head. Because of this, the static vent was introduced as a source of static pressure instead of the static head, pitot pressure then being sensed by a simple pitot head. About 90% of the combined pressure head position error is eliminated by use of a separate pitot head and static vent. A separate static vent is shown here. There is usually some place on the airframe, usually on the side of the fuselage, where true, or nearly true, static pressure obtains over the whole speed range of the aircraft. Earlier in this lesson, we learnt that whereas an aircraft on the ground in still air is subject only to static pressure, the leading edges of the aircraft in forward flight are subject to an additional pressure which we called dynamic pressure. This results in a total pressure on the leading edges of dynamic pressure plus static pressure, which we called pitot pressure. Expressed as a formula, it looks like this. Pitot pressure equals dynamic pressure plus static pressure, or P equals dy plus S. The pitot head senses pitot pressure, and the static vent senses static pressure. These two pressures are fed to the airspeed indicator, which is a differential pressure gauge, and it measures the dynamic pressure, which is the difference between pitot and static. Dynamic pressure is a measure of airspeed because dynamic pressure equals a half rho v squared, where v is true airspeed and rho is the density of the surrounding air. Thus, the airspeed indicator measures airspeed by measuring dynamic pressure, displaying the result, usually in knots, on a suitably calibrated scale. In principle, the simple airspeed indicator can be considered as an airtight box, divided by a flexible diaphragm, with pitot pressure fed to one side of the diaphragm and static pressure to the other side, as shown here. The pressure difference across the diaphragm is dynamic plus static minus static, which is dy, the dynamic pressure. Accordingly, the diaphragm is deflected by an amount proportional solely to the dynamic pressure, its movement being transmitted by a system of levers to the indicating needle on the face of the airspeed indicator. Note that static pressure is common to both sides of the diaphragm, and so does not influence diaphragm movement. In practice, as shown here, the static pressure is fed into the hermetically sealed instrument case, the pitot pressure being piped to a thin metal capsule capable of expansion and contraction. Note that the pressure differential between the inside and outside of the capsule is exactly the same as it was with the diaphragm in the previous diagram. Expansion or contraction of the capsule will therefore be proportional to the changes in dynamic pressure produced by changes of airspeed. The capsule movements are transmitted by a temperature-compensated magnifying linkage to the pointer indicating airspeed on the face of the airspeed indicator.